And so what quantum physics is essentially is we're quantizing on a very, very small scale. We can look at these very specific values that we have here, and in looking at an atom, it's very, very small values, right? We're dealing with these very small values that we see with the transitions of the electrons in the atom. And atoms are discrete. They don't always have the same amount of energy. Each atom has a different, energy level setup with, the different, we use the term orbitals. They have the different energy levels, and every atom's different. And as the electrons transition within an atom, they'll produce very specific wavelengths of light. Now, atoms can also absorb energy, and so they can absorb these photons as long as that photon corresponds to an energy level transition that's possible. And so in other words, if an electron is in a orbital in the nucleus, or around the nucleus, and there's a photon that comes in that matches the transition between that lower energy level and the higher energy level, it can absorb that photon and then jump to a higher energy level. And so with quantum physics, we focus on light again, and that's why we spent time in the last unit looking at what light is and how it operates, because now we'll be able to go further with this as we look at the atom. So we know that light is a wave. Light acts as a ray, but it also acts as a wave, and so it has a very specific frequency and wavelength, and we talked about that. In quantum optics, we use one equation from wave optics, and we know V equals frequency times wavelength, and so V equals frequency times wavelength. So C is the speed of light in a vacuum, and then we have frequency times wavelength, or wavelength times frequency, wavelength in meters, frequency in hertz, and we can determine, if we know 2 out of the 3, we can find the other one. And so what's crazy too is that light also behaves as a particle, and that's what Newton asserted, that light is a particle. But we saw all these wave properties as we saw in the last unit, and so it does have a dual nature, and this is kind of strange. And as we continue on, we'll see that too. And it acts as a wave. It also acts like a particle, and we'll look at the particle characteristics of it, because it turns out light has energy and light has momentum. Of course, it has energy, right? We know that, but light actually has momentum, and that's really strange, and we'll talk about that. And now a particle light we call a photon. That's one packet of light. And so as an electron transitions from, for instance, an outer energy level to a lower one, a photon of light is sent out. So we know that light is a wave. And so what's the relationship between frequency, wavelength, and velocity? Well, we know that equation, right? We know V equals frequency times wavelength. But how can we actually figure out what the frequency or wavelength of a photon that is absorbed or emitted? And so again, we have to focus in on what actual photon comes out, what kind of color comes out, or if it's outside the visible spectrum, what wavelength, what kind of energy does it have? And the key with this is seeing how with energy, in the electromagnetic spectrum, higher energy means higher frequency. So as you get further and further, in this direction towards, the gamma rays, eventually you get higher and higher energy, and you can figure out what photon actually is produced. So with resonance, this touches back to resonance, where electrons at very specific levels can receive a photon, but it has to be very, very specific photons, because they can't receive any, any particular photon unless it matches the energy level transition within the atom. And so, if an electron drops down, it will lose energy corresponding to that resonance and shoot out a photon that matches that. The photon will match that amount of energy. And so, if an atom receives a photon of light, and that's what I showed a demo in class, where the photon comes in and it matches something in the atom, and the electron goes from a lower energy level to a higher energy level, and that can happen as well. And so I like to show here with the black body simulation if you remember, and it would be good to remind yourself if it's been a while since you've looked at that with the blackbody spectrum. Remember, there's one very particular wavelength that corresponds to a certain is the predominant wavelength produced by something with a temperature. Everything with a temperature has electromagnetic radiation coming from it. And like for humans, it's not visible light. We have infrared, radiating out from our bodies. So you get to a light bulb, you have mostly infrared, but some visible light. And then with the sun, the peak wavelength for the sun, I believe, is the greenish bluish color. So depending on the temperature, will be a predominant wavelength. And so I'm going to have you go ahead and pause the clip and go ahead and read through the history here. It's important to see, the progression of this as we went through. So go ahead and pause the clip and take a look at this, and when you're ready, you can hit play to continue. Okay. So how do we actually calculate photon energy? We have a very, coming back again from Planck, we have Planck's constant, is really Planck. I just used to saying Planck. Planck's constant, 6.625 times 10 to the negative 34th joules seconds. This is in terms of quantizing counting up how much energy we have. And so with this is a discrete value. We can say, okay, based on how much frequency we have, we multiply by this value, and this is how much energy that actual photon has, 1 photon. And so we multiply the frequency of it times the Planck's constant, and we get that. Now, on your IB equation sheet, they give you this one. They do not give you the electron volt seconds one. So it's important to be able to go from one to the other. And obviously with this, you go from, you can convert joule seconds to electron volt seconds. You have 6.625 times 10 to the negative 34th joule seconds. And we know that 1.602 times 10 to the negative 19th joules is equal to 1 electron volt, right? Very small amount of joules is 1 electron volt. And we divide that value and we can get this value. And this is much more convenient to use because on the quantum scale, we're using something at very, very small scale. Again, frequency is also in hertz there for energy.